So as I was saying in the last slides, that the electron configuration can be done directly off the periodic table. So to start with, we have what we call the S block elements, and remember the S block is the first two periods, or first two columns of the periodic table, and I have all this outlined on another slide. The P block is the last six, right? So let's say you're doing the electron configuration for, let's say, silicon right here, right? Well, this is energy level 1, 2, and 3. So I can write the electron configuration of silicon because I know it's ending, right, in S2 or P2. I know it's P2 because this is P1, this is P2, P3, P4, P5, and then this is P6, okay? And you notice everything in a column, right, everything in the group has the same number of valence electrons, and so it has the same ending, like the letter and the number on their electron configurations. Furthermore, if you look at where silicon is on the periodic table, it's in energy level 3. So I know the ending configuration for Si is 3p2, and then I just have to backfill everything else. I know that's where I need to stop. So if I did chlorine, right, chlorine is in the fifth column of the P block, right? It's energy level 3, so it'd be 3, right, P, and it's 5 because it's in that fifth column. And then everything else backfills so that I'm full all the way up to that point. Now, we're going to go to this here, and this is how you know Aufbau principle without actually memorizing. This is 1, this is 2, and by the way, this shows all the blocks. So this is the S block, the D block, the P block, and the F block down here. So this is energy level 1, 2, 3, 4, 5, 6, 7, and maybe someday we'll get to 8 because this is a little bit old. This has all been filled out all the way down to here now. What we can do is doing the Aufbau principle. I know this is the S block, right? And I know that this is the P block. So Aufbau principle starts like this: 1s, and then it's 2s, and then it's 2p. Now in the third row, this is 3s, and then this would be 3p. So I'm up to here, right? 3s and 3p. Now, how do I know it's 3p? Because like, the periodic table, when you look at it, doesn't say that, right? It's because it's in the third, right, period in the P block, right? This thing is the P block. So then when I do the next row down, it's going to be 4s and then 3d and then 4p. So I'm taking care of this. Right, and the D's didn't show up after the P's, so they're one energy level down. So this is the thing you'll have to remember. A lot of times they'll say that this is n minus 1, because this is n, right? That column that I put on the far left as the periods of the periodic table, that's the principal quantum number for that level. So far I have 4p, right? And now where am I at? I'm at 5s, and then I'm at 4d, and then I'm at 5p, and so I've used these guys up. Okay, and then I can continue on. This is, let's see, 6s. I'm going to start down here because I've run out of room. Now, you notice there's a little asterisk here because you have to go down to the inner. These are known as inner transition elements because these are the transition elements. The inner transition elements go to the 4f's. So what you have to remember is this is n minus 2. You could also think of it as, well, I did the 4Ds, so here, I did the 3Ds here after the 3s, right? So then what's the next orbital that would slip in? It would be the 4Fs. It's from energy level 4, actually, right? So there's 4S, 4D, 4P, 4D, and 4F. Most people just remember n minus 2. 4F, 5D, and then 6P. Again, I did this here to here. So I went like this, right? And then I came back to here, and then I'm going over to here. So that's how the order is done. And then I have 7s after that. So I have 7s, and then 5f, 6d, and then 7p. These would be the 7p orbitals that are down here. Like I said, this is a little bit old. Those have all been filled in, and I believe all of the elements have been verified down in that region of the periodic table. So that's the entire Aufbau principle for every single element that is naturally occurring and the ones that we've made. So lots of these are man-made in the regions of the 5Fs, and also all of these guys in here are all man-made elements. So anyways, so you don't need to know the Aufbau principle. I'll show you one other trick which I will discourage you from using because I find it to be more confusing than it is useful. Okay, so this is right off Wikipedia. If you Wikipedia Aufbau principle, you get this. And so what you do in order to get the Aufbau principle is you draw this triangle, and you see what I've done is put all 1, 2, 3, 4, 5, 6, 7, and then I've done P's, D's, F's, and then over here would be G's, like 5G. So you know, you can go further, right? So this would be 5G. They don't show it. This would be 6S, 6P, 6D, 6F, and 6G, right? And if I want to do the Aufbau principle, I can take the time to draw this triangle out, and then I can go 1S, and then the arrow comes back to here, and it goes 2S, and then I go back to here, and I go 2P, 3S, and I take the arrow, go back to here, and it's 3P, 4S, and it's 3D, 4P, 5S, and then it's 4D, 5P, 6S, and it's 4F, 5D, 6P. But I often find that by the time I would have done that, I could have looked at the periodic table. And the periodic table would have just told me, oh yeah, it's this, and then it would have been done. Okay, so for example, if I had an element that was in the 5Ds, I wouldn't bother to draw all this out. I would just go over to my periodic table. And I would have, again, when you're doing the electron configuration, you'll have the element. So let's say you're doing the electron configuration for mercury. Like it's here. Oh, it's a bad highlighter color. Let me get a better highlighter color. We're going to do electron configuration for mercury, right? Well, in order to do mercury, you'd have to draw that triangle and go all the way down to there. Or you could simply remember that this is 6S, right? Down here, this is 6S because it's energy level 6. This must be then 5D10. So that's what it's going to end as. So I'm going to say 5D10 is the end. And then what's before 5D? Well, it's this guy here. So that's my 4F. And then what comes before the 4F? Well, that would be, again, I'm backing up. It's the 6S. And what comes before the 6S? Well, I'm going to use core notation. There's no way I'm writing all that. So I'm just going to go core XE. So at the time that you could have drawn the triangle, you could have also just done that. If you can remember that these is D and it's n minus 1, or this is F and it's n minus 2, and this, all of this on the left-hand side, those are the n values, principal quantum numbers. That's a lot easier, I think, than drawing that little triangle. Okay, oh, and a lot more, time efficient, and also based on the periodic table, the little triangle is just a happy coincidence that it works out, right? It doesn't have a meaning, whereas looking at the periodic table helps you learn how to use the periodic table. Okay, so we're going to actually use the periodic table to do some electron configurations. Indium and niobium and bismuth, and we're going to be using core notation. Because life is too short. Okay, so let's go ahead and do core notation for indium. I need to jump over to the periodic table and find it. And I'll be working these out actually on this slide, and then later I'll just have them all written over on the other slide. It is the best to do this with the periodic table right in front of you. So here's indium right here. Okay. So if I'm going to do indium, I have to think about how its electron configuration ends. Then I just need to back it up until I get to the noble gas core, right? So indium is in the principal quantum energy level of 5, right? That's what this is telling me. And this is the p block, and it's the first element in the p block. So its electron configuration is going to end as 5p1. Then what I have to do is I have to recognize this is all filled. In order to get to this position, this is all filled. And so that's 4. It's n minus 1, so it's 4d. Oops, I didn't leave myself room. And I'm only writing it backwards because it's easier for you to learn it that way. But in reality, when you're doing it, right, you'll be going in the forward direction. You'll identify this, and you'll say, well, I'm going to start here at rubidium and work my way over to it, and then write the core, right? So then what that takes care of this whole central section here, right? So then this is 5s2. And then brackets around kr. And so that would be the electron configuration of indium. Now, if you doubt that that's like the right way or the right one, right, it's pretty simple to check. Kr is 36 electrons, right? And then I have 2, 3, I have 13 more. So that should get me over to 49 total electrons. So that would be the electron configuration for indium because that comes out to be 49. And the next one would be niobium, Nb. So again, we got to go find that on the periodic. And where is it, right? Element 41. So it's right here. And we'll do this one the way you should be doing it by now, hopefully. You'll notice that it's in principal quantum energy level 5. So that's 5s and that's 4d. So I'm going to start with the core. We'll say Kr. And then I'm going to work my way over to niobium. So it would be 5s2. And then 4d3. So 1, 2, and 3. Right. Now, I'm going to point out in the next slide that there's lots of exceptions in the transition elements. They may come up on a quiz or a test or a final exam, for example. You're not supposed to be looking it up to get the answer, because when you look it up, for sure you'll get the properly analyzed niobium electron configuration. And they do that using spectroscopy to see where the electrons actually are in the structure. You're supposed to do the things that we're doing right now to find electron configurations, because by far the ones that follow the rules that I've taught you are the majority of the elements, and there's very few what we would call exceptions to those rules that we're teaching you. Okay, so just sort of like as a warning, make sure when you're doing these, you just follow the rules. If it's an exception, I don't expect you to know any of the exceptions. I might expect you to know why exceptions occur at different places, but I just want you to give me the electron configuration that you would expect to find, assuming that Aufbau principle is true, Pauli exclusion principle is true, and Hund's rule is true, okay? And Hund's rule is really for orbital diagrams. You wouldn't see that in the electron configuration. So this would be the electron configuration for niobium. Krypton is the core, right? Now that's different than the core electrons. The core electrons would be krypton plus the 4d3, so it would be, I guess, 39 electrons. But the core, like the Nobel gas core for core notation, right, is krypton, and it's 5s2 and then 4d3. So the next one to do is bismuth. And so again, we've got to find it on the periodic table. And then we'll use core notation. So let's see, where is it on the periodic table? It's way in the heck down here. Right? Bismuth is a really interesting element because it alloys with a lot of metals and causes them to have interesting properties. And it's shiny. It makes these beautiful crystals. If you want to YouTube something that's cool, look at bismuth crystals. And people make these at home just for fun. You can buy big chunks of bismuth. Anyways, it's a little bit dangerous, so you should know what you're doing. Like finish this class and then ask me about it. All right, so yeah, so bismuth is 83. The core is xenon. So I'm going to work from xenon now. And then I'm going to go down to this energy level, right? So principal quantum number 6, right? Or energy level 6 or 6th period. So it's going to be 6s2. And then after 6s2, I'm going down into the Fs, and that's the first group, 57 to 71. So that's these guys. The lanthanides is what this is called. So this is going to be, again, n minus 2, 4f, right? 14. There's 14 elements down there. And then 5d, that's this. 10, because it's filled. And now we're to 6p, because we're back on the energy level, right? Here. Right, so these are the 6p, and then there's, I'm in the third column, right? 1, 2, 3, so it's 6p3 like this. So that's your electron configuration for bismuth. So I hope you'll be able to do that now just by looking at the periodic table. Again, you know, as you're doing the homework, use that and practice it. Don't just be looking it up. Make sure that, and don't be just trying to do that triangle thing or just memorizing the Aufbau principle. It's just a lot easier to do that off the periodic table. All right, so let's talk about some oddities or problems in the transition elements. In the main group elements, I don't believe there are any exceptions of the main group elements to the rules that we just taught you. But for the transition elements, what we find is there's a number of different places where you find exceptions. So scandium, let's just put this in perspective. This is scandium, right? Oh, shoot, can't see my pointer. Hang on. Scandium here, we'll go back to our periodic table and see where it is. So it's actually in the 3Ds. So we're right here, so 4s 3D. And so we're looking at this first row of the transition elements. So we would expect this to be 3D1, right? This would be 3D2, 3D3, 4, 5, 6, 7, 8, 9, and 10, right? That's the expected electron configuration. So this just shows what they actually are. So scandium, yep, it's 4D1. So I mean 3D1. Here we go. It's got a better highlighter. And then 3D2, and then 3D3, and then notice what happens at chromium. This is the first column that we see exceptions. And the reason there's an exception is it's better to have, well, let me give you a little bit of background before I just tell you flat out what the reason is. If you remember, in generating the Aufbau principle, the 4s and the 3Ds were very close in energy. So this is where we were, is 4s, and then 3D is here, right? So what I'm doing is I'm taking electrons, right? I'm going 4s in that scandium. It was like this. Scandium was this. And then I'm adding electrons to it as I'm moving to the right. And then what happens when I get to chromium is it's doing this. And there's a couple of things that are going on here, but it turns out a half-filled energy level tends to be more stable than one that's not half-filled. And this effect becomes more important as you get more electrons into it. The other thing that's going on is we have some pairing energy that would go on if chromium looked like this. So this is chromium with pairing energy. And so if I take this electron out, I can get rid of that pairing energy. And then this stabilizes the 5d orbitals, the 5 3D orbitals, let's say it that way, the 5 3D orbitals. And what do we mean by stabilize? It means it lowers their energy. And so what happens is these switch places, that this drops down and now is below the 4s. And so that's why the electron goes over here, because this is dropped low enough in energy that it is easier to put the electron in the Ds than to keep it in the 4s where you have that pairing energy. As you move up the periodic table, or down the periodic table to energy level 5, 6, 7, 8, these energy levels end up getting closer and closer together, and that's why we see a lot of switching around in the electron configurations. So we're here with chromium, and there's an exception, and it turns out if you look down at molybdenum, it's the same thing. Again, the 5s and the 4d are very close in energy, so it's able to do this and actually make the atom more stable. There's actually a thing that goes on with the actual orbitals. They actually shrink in size because they become more stable by having the fifth one in there. So you see some weird things in their radius trends as well. Manganese, that you're going to have to pair in either the 3d orbital or 4s, so it goes back to normal. So this looks normal here. This is normal, right? This is normal, that's normal, that's normal. And then all of a sudden copper, same thing, right? There's a weird spot in the transition elements right at copper. And what copper's doing is actually, again, stealing electron from the 4s to completely fill the 3d subshell. And filling a subshell, just like filling the energy level, gives it some stability. Again, that just means these are lower in energy, and so you're able to stabilize these 10 electrons versus this one. And then zinc again is normal. Now again, like I said, the energy levels get closer and closer together, so now what we do is we move down, right? And what do we see? We see 4s2, 5s2, 4d1, that's normal. This is normal. This is the first exception. This is the second exception. Again, it's that pairing energy of the electrons, right? So in this period, again, let's go look at the periodic table. We're here, right? And moving along this period here, we're going to see more exceptions because, again, as you go to higher energy levels, remember the Bohr energy levels, how they got really close together? These are getting closer and closer together. So there's going to be some switching that goes back and forth. Again, this one's normal, thank goodness, and then already we have exceptions here. All along this bottom row, these are all exceptions, right? But this really only occurs in the transition elements and the inner transition elements. And for the main group elements, essentially it obeys what we expect it to obey. I expect you to be able to give me the expected values, right, and not the experimental values. And so I've just picked a bunch of them out. Again, there's more than this. I just picked a bunch of them out to sort of illustrate. I would expect you to give me something like this, but then if I told you like palladium is like 4d10, I'd want you to come up with some sort of reasonable explanation why 4d10 would be the electron configuration and no electrons in the 5s. And the simplest explanation is the energy levels are close together, right? But by filling the 4d subshell, we stabilize the 4d electrons, and so they drop lower in energy than the 5s. Like between 5s and 4d7, we might expect that to happen if you knew that this is what happens, right? This is not half filled or filled, but there's pairing energy in the 5s, and so apparently it's easier to put the electron in the next higher into the 4d energy level. A couple other bits about the electron configurations. The properties of elements follow a periodic pattern, and the quantum mechanical explanation is that that's because they have the same number of valence electrons, so you would expect the same kind of chemistry to happen with them. In periodic law, we say, right, elements in the same group have similar chemical properties. These properties repeat at each period, and I guess it should add in there when the atoms are placed in order of increasing atomic mass. But quantum mechanics predicts this simply based on the number of valence electrons. One more thing too about noble gas electron configurations. These are all listed for you in your book like this kind of nicely. They all have 8 valence electrons, which except for helium, because he's so small, he only has 2 electrons, but that fills its subshell. we say generally that the noble gases are inert. This is the term that we use, right? Because they don't react. But what really that means when something is inert is that they're happy where they're at, right? So they're non-reactive because they're stable. So quantum mechanics actually makes this prediction because filled shells and subshells tend to be more stable, and the noble gas has both of its subshells filled to fill its valence shell, right? And that gives it its extra stability. Now, it also turns out that what quantum mechanics would predict is elements that are close to these elements, right, would be more reactive because what they tend to do in their reactions is go to electron configurations that produce noble gas electron configurations. So what groups of elements are the most reactive? So we got to go to our periodic table again. The noble gases are here. And so it's pretty easy to see that the halogens being right next to those are very reactive, simply because if each of these halogens was able to pick up one electron, then they would assume the noble gas configuration and become more stable. But the other group that's really important to recognize is the one that's all the way over here. Group 1, right, is the most reactive metals group, because if they lose one electron, right, if you lose one electron, then you also can be like a noble gas. So when lithium loses an electron, it becomes like helium. And when sodium loses an electron, it becomes like neon. And if you remember the video that I showed for the reaction of sodium and chlorine gas, it was violently exothermic. We looked at that before. And so that's just one of those things that comes again from quantum mechanics predicting that this group would be the most stable. It also predicts that the groups next to it would be the least stable. And this slide is just a summary of what I just said about alkali metals losing one electron and halogens gaining one in their reactivity. So here's a check to see if you understand the concept. I like this question. It says a main group element has an outer electron configuration of Ns2Np4. What is likely for an ion of this element? So Ns2Np4, right? That means it is got 6 valence electrons, and the noble gases all have 8. All right, so which is most likely to happen? To lose 6 electrons to become like the noble gas that is to the left of it on the periodic table, or to gain electrons to be like the noble gas to the right? Well, since you only have to gain 2 to have an octet, to have 8, then most likely what's going to happen is it's going to go from Ns2 to Np4. It's probably going to go to Ns2 to Np6 by gaining 2 electrons. Well, if it gains 2 electrons, the most likely ion for it to make would be a -2 ion. When we look actually at the periodic table, the elements that have 6 valence electrons are in this column here. And from what we learned about in formation of ionic compounds, right? Oxygen, sulfur, selenium, tellurium, all these metals and semi-metal tend to pick up 2 electrons to form -2 ions. So oxide ion is 2-, sulfide is 2-, selenide is 2-, etc. So this comes again as one of those predictions from quantum mechanics that if you can pick up 2 electrons to achieve the noble gas electron configuration, what you end up having is a more stable ion, and that's the tendency for all of these elements in this group. These elements, these would be Ns2Np3, tend to pick up 3 electrons, and this is Np2, and picks up 4 electrons to become like neon. So again, all the anions that we see, which we predict based on their position on the periodic table, that prediction is because of their electron configurations. This is also a figure from your book. These are the ions that form predictable charges. So we already talked about these. They didn't put carbon on here for some reason, but carbon has a predictable charge as an anion. And scandium also has a predictable charge. So some of the ones that are missing from what your book said, scandium 3 plus and carbon 4 minus. In particular, the one that people think about is something called calcium carbide, which is what's used in miners' lamps. And then aluminum also can forms only a 3 plus ion, and that's based on the electron configuration. And then below aluminum, we have gallium and indium. And these are actually predictable from their electron configurations too, because typically it's the highest energy level electrons which are ionized off of the atom to form the ion. So in the electron configuration for gallium, gallium is 3s, sorry, 4. I don't know why they have 1, 2, 3, 4 over here. That's what I started going off of. That's actually an error. Hydrogen's in period 1, so you can ignore all this. I just never noticed that before. But gallium is 4s2, 3d10, and then 4p. That's a 10. This is for gallium. 4p1, and if you ionize the highest energy level electrons, that would be those, right? And so that's how you get the +3 ion. Again, something predictable based on quantum mechanics and electron configurations. And indium is exactly the same sort of behavior. Perhaps a little bit more difficult if you just wanted to finish this chart out. All the predictable ions are actually including these transition metals. These are silver and copper, zinc. These are 2 plus ions, and then silver, which is 1 plus. Which you can see why they were given the numbers 1b and 2b when the periodic table was expanded to form the periodic table with the transition elements in it. And then scandium is also 3b. Again, these numbers that are here, which aren't in sort of the more modern periodic tables, are an indication of their chemical reactivity because that's where they were placed in the old periodic table when the transition elements before the discovery of the atomic numbers were placed with the rest of the elements on the periodic table.